Hello, everyone. Can you hear me at the back? Excellent. Well, nice to see so many of you here. I'm just going to have a few remarks. I'll keep these pretty short. I guess the most important thing, really. Okay, not be able to advance the slides. Is to say welcome. I know that it's been a bit of an ordeal. This workshop was supposed to have happened about 3 years ago. COVID has interrupted that a couple of times now. So it's really nice to see so many of you here in person. There are people online as well, but I'm really pleased to see so many people in this room. Okay, and I know that it wasn't trivial to get here. I mean, no doubt there will have been some degree of travel chaos. Even traveling from about 100 miles away, I found some travel chaos. And of course, the period of national mourning, we know that was a very sad event, but that will have undoubtedly had an impact on you. Possibly you had to go hunting, gathering yesterday to find something to eat, for example, since many of the shops were closed. So just let me pause briefly to say thank you to the Isaac Newton Institute. Without them, we couldn't have this meeting. Thank you for the various INI staff who've helped organize so much. But mainly, I would say, thanks to you lot. Okay, we wouldn't be here if it wasn't for you. And I'm looking forward to having a great week. I think we know why people care about sea ice, so I'm going to skip over a few slides because I don't want to lose too much time. I think the microphone's needed for the people online. Right. Is that any better or worse? Okay. Okay. A, B, C, D, E, F, G. How does the rest go? I forget. Okay. So we all know why people care about sea ice. Okay. The general public are interested in like the golden age of exploration. Those of you who've seen the Frozen Planet, is this working at all? Okay, those of you who've seen the Frozen Planet will see there's a huge amount of interest in wildlife in the Arctic and indigenous communities, and increasingly it's been important for shipping. I just want to throw it out there that sea ice was a platform for the Cold War in the past. Of course, this would be totally unthinkable nowadays. So moving on to perhaps why some of us here are interested. Sea ice is a fundamental component of the climate system for many reasons. Okay, but of course, sea ice has been dramatically changing over the last few decades, which has captured the minds and hearts of people of scientific bent and politicians and the general public. That change is having huge impacts locally in the polar regions, of course, but it also has the potential to affect us at whatever latitude we may happen to live in, whatever civilization we may think we have. It has the potential to be strongly affected by the loss of sea ice. And we'll deal with that over the next 2 weeks. So mathematics is instrumental to studying sea ice. It's a complex, multi-phase, multi-component material with morphology ranging from millimeters to megameters. Okay. Some of the shout outs to some of the theory that's involved, musculature theory. Okay, I see Gray Worcester is lurking at the back. So he's one of the chief architects of musculature theory, has various of his students have gone forth to spread the word. Critical connected pathways for fluid dynamics, fluid transport, the famous law of fives, etc., and other emergent phenomena. The rheology of sea ice is complex and poorly understood. We have a huge selection of talks on that as well. Okay. And increasing there's interest in discrete element models of sea ice as, well, for various reasons, partly due to computer architecture, but also partly because the elements of sea ice, the sea ice flows, are actually of comparable size to the numerical resolution of continuum models. So there is some concern about the legitimacy and, I guess, more practically the efficacy of these continuum models at such high resolutions. Many sea ice processes defy direct numerical simulation. So a lot of work in sea ice is to do with mathematical modeling and parameterization development. Much of my own work is along those lines. Particularly topical, I feel, given that the state of the Arctic is changing. It's become increasingly marginal, opening the field for new areas of research. Analysis of simple models, toy models, and complex models of various kinds is necessary to disentangle the various nonlinear interactions and feedbacks. And as the Arctic is becoming relatively ice-free, people are increasingly interested in navigating across it, okay? And so ice weather prediction is becoming increasingly important. And so this opens the field for optimal use of data in real-time forecasting, and data assimilation is an emerging area. Okay, just to say that building understanding of sea ice, a physical mathematical understanding, requires many disciplines, requires a combination of observations, theory, and models. Not all the talks we're going to see over the next 2 weeks will seem mathematical, okay? There may not be many equations in them, for example, okay? But actually, this is essential material for developing the models, and much of the thinking, for example, of analysis of climate models is essentially mathematical. Moving on to housekeeping briefly. Talks are streamed live, which is why you need a microphone, okay? If you're using this laptop, it already has Zoom set up for streaming. So that might be the easiest thing if you can, to put your talk on this is my one, okay? This is the Isaac Newton one, you can't see it down here, okay? Putting your talk onto that, it might be the easiest thing because it's automatically streaming. If you're in the room and you're connected to Zoom, which for example, you might be if you're chairing a session, okay, you need to see what the questions are, you should turn your microphone off and turn the speakers down, okay, because otherwise there'll be feedback. Yeah, okay, so the talks will be streamed live. They will be recorded and made available later. You should have had a form about this, okay? If for some reason this isn't okay, and I know there might be secret information, for example, particularly possibly relevant for next week, that's totally fine. You just got to let us know and we can sort that out. Okay, so this week is mainly going to be environment and climate modeling and mathematics and theory. Next week is mainly about industrial and engineering aspects. So I think that I'm going to leave it there to hand over to our first talk. And I think I'm just about managed to claw back some time. Oh, and our first talk is by Elizabeth Hunke.
I have it on. Test.
You won't hear it because it's not in front of her.
Okay, I'm going to get this out of the way. That's not mine. I'd love to talk about that, but I have no idea. Okay, thank you. Okay, so Danny asked me to give an introductory talk about sea ice and in particular about modeling it. And so the first part of the talk is going to be very introductory, like sea ice 101. And hopefully you all know this already, but I'm going to go through it very quickly just to kind of set up the rest of the talk, where I do want to talk about the connections between models that were designed for simulating climate and shorter term forecasting needs. So I'll begin by pointing out that there's basically 3 different communities of people that are interested in models like this. There are scientific researchers who are interested in the processes, internal to the sea ice or how they interact with the atmosphere and the ocean. Then there are climate modelers who are interested in very long-term studies, into the future or maybe into the past. And then there's a third group, which is interested in the shorter term forecasting. How do we predict what's going to happen in 2 weeks? I currently lead the SICE consortium. SICE is a sea ice model, and the members of the consortium are from all 3 of those groups. And so I feel like I have kind of a unique perspective on how that interaction can happen. And so that's what I'd like to talk about today, is a little bit from that perspective. But I will say there's another group of people who are interested in the output from these models. And that's the people who are out there on the ships, the mariners. I don't interact directly with them. There's an interface there, but they have particular needs also. And we'll try and bring some of that out today. Okay, so I'm going to start with a very, like I said, Sea Ice 101, but it's going to be very brief. I want to spend more time on what we think might be needed for the modeling and some considerations having to do with the time and space scales. So first of all, I hope you all know sea ice is frozen seawater. It's not land ice. It's land ice is frozen snow or compacted snow. So sea ice does have a horizontal area. At any given time, it covers maybe 4% of the Earth's surface, but that's pretty small, but it still has a big impact. In addition to having a horizontal extent, it has a thickness. The thickness is much smaller than the horizontal extent, 1 to 2 meters for young ice, but it can ridge and build up into ridges and keels that are maybe 10 meters, maybe more, maybe less. I'll keep going. This one has I don't know how you do this. Uh-oh. Okay, well, this one has video, but the sea ice is also in motion, and climate modelers at least don't try to simulate or represent individual ice flows. That's too much for us to do. Our goal is to represent the large scale circulations in the basins. I have a note here just to make sure that you're all not sleeping. I want to very quickly ask you to raise your hand on these 3 topics if you think mariners would care what the horizontal extent or the ice coverage is for sea ice for their operations. Do you think they would care? Raise your hand. Okay. Do you think they care about the thickness of the ice? Oh yeah, okay. Do you think they care about the motion of the ice? How fast it's going, that kind of thing? Yeah, it's fewer people there, but still, I'd say about half of you. Okay. All right, as it's moving around, the ice is carrying things with it. So in this picture, it looks like there's soot, dust, I don't know, who knows, on top of the ice. There's also liquid water on top of the ice and various things. And so it's moving around. As the sea ice melts, it drops those things into the ocean, and that can affect the ecosystem. And of course, sea ice also has things inside of it. This is an ice flow that's turned on its side with a layer of algae inside where the solar insulation has absorbed a little bit more. It kind of rotted the ice. And so when the ice turned on its side, this upper layer, which has snow on it, slid off. That's what you're looking at here. But you can see there's actually algae down inside the ice also. This is in the Antarctic. And here's another signal to me, vote. Do you think mariners care what the ice is carrying around with it? We have 1. Okay, very good. All right, so what's important depends on what your interest is, what your particular scientific field of study is. That's what you're going to say is important, right? If you happen to be a climate modeler, it's the albedo. Oops, wrong button, sorry. Okay, If I can use this thing. All right, so for a climate modeler, what's important is this difference between the surface of the ice and snow, which is very bright, and the surface of the ocean, which absorbs heat and melts the ice back further in the ice ocean albedo feedback, which I'm sure you've all heard of. The other thing that's really important for climate modeling is the volume of the ice. And Marika had a very nice illustration of this in a paper a while back, where these are all different models from CMIP, and I don't know which CMIP it was. It was a while back. But these plots are showing the sea ice concentration in September on the vertical axis. Here it's plotted against year in these simulations, and in here it's plotted against the ice thickness. And so what we see is the models that have very thick ice tend not to lose it over time. And the ones that have very thin ice do tend to lose it over time. So that's very important from a climate modeling perspective. And then finally, this is Danny, of course, mentioned this, the sea ice is changing. And this is a large part of the reason that we care about sea ice, because it's changing. It's thinned by half, maybe more, since the 1980s. And the extent is regularly outside the range of variability, even from 10 years ago. So that's a basic introduction to what sea ice is. Hopefully there was nothing new there for any of you. But now I want to talk about some of the important processes and an introduction to how we model them in Earth system models. So first of all, there are a lot of different processes in these models. Many of them can be represented in a single column. You know, they're not affected by what's going on in the neighboring grid cells directly. And I'm going to come back to that. First, I want to talk about the dynamics of the ice. This is in the dynamical core, which essentially consists of 3 equations. And Danny, sorry, I don't have a lot of equations in my talk, but there is a momentum equation that gives you the momentum, the ice velocity. There's a rheology, and then there's a set of conservation equations that describe what's being transported across the surface of the ocean with the ice. And the rheology is a constitutive equation. It represents the mechanical properties of the sea ice and things like the strength of the ice, how it changes when it deforms, you know, just kind of what that looks like. And there's various ways of representing that or describing that. And during this workshop, you're going to hear about a lot of them, I think. But there's continuum models. There's also discrete element models that look more like ice flows, but they're generally not individual ice flows. So we'll be talking about some of those during the workshop. One of the improvements to these climate models recently is landfast sea ice. And so here's an example from a sort of a standard rheology model, the viscous plastic, where in this area near the Siberian coast, the model's just not able to simulate landfast sea ice. That's ice that's stuck, right? It's not moving. In viscous plastic model, it's basically always moving. And so the Canadians really needed to fix this. They wanted a landfast ice in their model. And so they used one of the characteristics of sea ice that causes landfast ice, which is that the keels can extend so far down that they hit the bottom of the ocean, and that pins the ice in place. And so they put in a parameterization related to that and put that in this ice model and ran it. And actually the simulations look absolutely great, I think. This is a plot of the frequency that landfast ice occurs in the model compared with the observations. But it depends on being able to simulate the ridges and the keels. And so here's something that we're actually working on in the model. It's not quite there yet, but we've done the theoretical work for it. Andrew Roberts did this. So let me back up a minute. In the models, when you're ridging ice, the basic idea is that you're changing the kinetic energy of the ice converging into a gravitational potential energy of the ridges and the keels as they build. So Andrew took a step back and looked at this from the point of view of Lagrangian mechanics and soil mechanics, actually. And so what he was thinking about is that the ridges and the keels underneath, think of those like piles of sand. If the angles are too steep, the sand's going to kind of roll down the sides until it reaches an angle where that's stable. Okay, and so you can do this with sea ice, treating the ridge as one of those piles and also treating the keel as one of those piles. And this is a minimization problem. It's in a floating piece of ice, which makes it even more interesting than soil mechanics. But you can do this, and when you actually do it, the comparisons with the observations are fantastic. So the theory is done. We don't have it in the models yet. And actually, I want to put an advertisement out. If you know somebody who's going to be looking for a postdoc position, maybe come talk to me, because I would like somebody to do this. Okay, so let's come back to the column physics, which I've represented here. I call that software package ice pack in my model. But this can includes all kinds of things like thermodynamics. There's melting and growing ice. There's a hydrology of the ice, like the liquid water that's on top, brine drainage, water percolating through. There's morphology of ridges and keels. And then there's a lot of other things on here that are not basically inherent to the sea ice model. They're not specifically sea ice processes, but the sea ice model needs to be able to handle them in order to couple with the other aspects of the Earth system model, like the atmosphere and the ocean. So the important thing about thermodynamics is that the growth and melt rate is a function of the gradient of temperature with the vertical gradient of temperature. So when the ice is very thin, this gradient gets very steep. And there are a lot of different thicknesses in the in any given grid cell. So to handle that and all the different growth rates that you might see, we have a thickness distribution in the grid cell. And we tend to collect the bins of ice thickness categories down toward the thinner ice so that we better resolve that gradient. Now, in climate models, this ice thickness distribution typically has 5 thickness categories. That's not very many. This is, in fact, a thickness distribution in the mathematical sense. There's a mathematical definition for it. The models are not limited to 5 categories. You can use 12 or 20 or whatever, but for climate modeling, you want to keep things not so expensive computationally, and so we tend to use 5. But the thing is that well, each thickness category has its own characteristics. It has its own thickness of snow. It has its own the forcing from the atmosphere at the top. It has its own thermodynamic profiles through it. So this is essentially increasing the resolution of the model because we have all these calculations in each grid cell. And G is the symbol for the thickness distribution. I don't have the full equation up here, but this equation, if it were up here, is actually the fundamental equation in the entire sea ice model, because it integrates all of the processes in the model into the final output, which is the thickness distribution. So one of the other really cool things that has gone into the model recently is a flow size distribution. Is Letty here? I think Letty. Oh, she, okay. All right, so Letty Roach did this. She extended the ice thickness distribution with a radius of the flow sizes. So she generalized the ice thickness distribution. And this is really nice because as the ice is retreating now, the waves can penetrate farther into the ice pack and move them around, break them up, change the sizes. This has the potential to change the interactions between the ocean and the atmosphere in ice covered regions. So this is very exciting. And then finally, one of the things that's really driving ice model development in the climate community is the ecosystem. And that's because climate models have become Earth system models. And that change in nomenclature is partly political, but it's partly, mostly, because these models now include chemical and biological cycles, like the carbon cycle and the phosphorus cycle and, you know, algae and nitrogen, those kinds of things. And so since sea ice is part of that overall Earth system, we need to include it in the sea ice also. But this is challenging because most of what's going on in the ecosystem in the sea ice is happening within the brine. So sea ice is this mixture between ice crystals and liquid brine. And that's where stuff is happening. So we needed to be able to represent how that brine changes in the ice. And so that drove our inclusion of mushy thermodynamics. Okay, so mushy just means it's this mixture between the crystals and the liquid. And the mushy thermodynamics basically consists of 4 equations. There's the conservation of energy, conservation of salt. There's a relationship between the fraction of ice crystals and the fraction of brine that's in the ice. And then, oops, I keep hitting the wrong button, sorry. And then there's some representation of the velocity or the flow of the brine through the ice. Because of the strong gradient between the relatively warm ocean and the very cold atmosphere, the processes here do tend to be vertical. And so these brine channels form, and as the ice gets very warm, they open up, becomes very porous. And so you can, this can cause the melt ponds that are on the surface of the ice to drain out, or seawater can flush up into the ice. And that's what feeds the ecosystem. So that's a very, very fast overview of sea ice and what we have in the models. It's not complete. There's a lot of other stuff that I haven't mentioned. But sort of the point here is, for one thing, the ice models have become quite complex. They do have a dynamical core. There's a bunch of column physics, and everything that's in those column physics parameterizations have to be transported with the ice. Okay. So that's kind of what the ice model is as a whole. And I wanted to give the opportunity for any questions on that before I go on to the next one, which is what we think models might need in the future. Any questions? Okay, I'm preaching to the choir, I think. Yeah. All right. Okay, so I do lead the SICE consortium with these various members of the modeling community in it. And so I took a very informal survey of my SICE consortium people, and I asked them, what do you think is going to be important in 5 or 10 years or 20? And of course, their answers depended on what they were working on. But I don't know, this wasn't too surprising to me. The climate modelers are, of course, very interested in the biogeochemistry because we need the ecosystem aspects as part of the full Earth system. The climate modelers, especially at the Department of Energy, are becoming more and more interested in what's going on near the coast. So the landfast ice is part of that, but there's some other aspects to it that we're also interested in. Of course, the ridging is important near the coast, so it's not surprising that that came up. Seems like everybody is interested in predictability and forecasting of some sort, not necessarily seasonal, but forecasting in general. And my personal contribution to this list is that I think we need to improve the atmosphere and the ocean models, but that's my opinion. There's a lot of interest in data and better ways of incorporating the data into our simulations. So that can be through data assimilation or using artificial intelligence, machine learning, those kinds of things. And then finally, something that's not mentioned very often, but for all of these applications, we need the models to run relatively fast, because we either need to do really long runs or a lot of runs or very highly resolved runs that are shorter, or maybe all of those. So that's what the consortium thought. Now, I did a second survey, this one not of people, but I went to the agenda for this workshop and decided, okay, so what do people think might be important here? And the overlap was not very big. The ones that are in white are the ones that I thought overlapped. What I thought was just kind of interesting. It's a different perspective. Of course, this workshop was not intended to be all inclusive. You wouldn't expect it to be, and it definitely represents the interests of the organizers, which is fine. So I grouped the titles from the agenda into topic areas. And what I saw, at least, is that there's a lot of interest in the sea ice dynamics, 9 talks. That includes the landfast ice. If you combine the wave ice dynamics with the flow size distribution, because those are very closely related, that's a strong contender for what this workshop thinks might be important. Then, of course, there's a few talks about ice-ocean coupling. There's a few about melt ponds, which might be considered atmosphere ice coupling, predictability, some data, and various other things. Okay, so let's talk about just forecasting in general. The big picture is that there are a lot of time and spatial scales, very far out, 50 years, 70 years, 100 years. You're looking at standards and regulations, or maybe planning for infrastructure. On very short scales, there's just the operational needs of the mariners themselves being out there. And those are very short, a few hours, 300 meters resolution or better. There's no way a climate model is going to do this. Climate models do tend to be used for these longer scales, but they have a lot of trouble spanning these time scales. So in this talk, I'm of course most knowledgeable about the climate modeling, so that's what I'm going to talk about. But for using models that were designed for climate, I do want to distinguish between 2 different use cases. One is actually using the simulations, the longer term climate projections, and analyzing those to try to predict what might happen at some point in the future. And actually using a model that's designed for climate studies to make shorter term forecasts. Those are 2 different things. Okay, so I'm gonna talk more about the first one, but come here. I'm gonna have a cameo appearance to talk about the second one from Ed Blockley. Yeah, and yes. Oh. How about
this one, Mikey?
Cool. Thank you. So yes, at Met Office, we're one of those people that use the model for everything. We do climate prediction, which I'll be talking about a bit later on, but we also do operational forecasting. And I'm also involved with the ice charting, International Ice Charting Working Group. We don't do a lot of ice charting in the UK, so I'm more of a voyeur on that group. But I just want to say briefly about ice charting. So as well as the modeling and the forecasting people, there's this whole ice charting, which is incredibly involved and complicated processes done mostly in the countries that border the polar regions, and they will every day. So down in the bottom right here are some ice charts produced by the Norwegian Polar Institute, Met Norway, and these are made by humans that are mostly you can see here on, I don't want to, things that they will use. Typically they'll use synthetic aperture radar, visible satellite observations. They're not really that keen on using the passive microwave products that we typically use for climate studies and in our forecasting models, and they will use model forecasts, but they're not that keen. And actually Nick Hughes at Norwegian Ice Service has said to me he'd rather use 3-day-old SAR than use a model or a passive microwave data, which I was particularly happy to hear about. Anyway, the Ice Charting Working Group, International Ice Charting Working Group, have this Mariner survey, which is the main thing I was going to mention about mariner needs. So these were actual ships captains and senior crew that have been asked, what do you want to know about for sea ice? So most of the majority of the responses came from ships captains, and most of them had 10+ years polar navigation. So these guys know their stuff. And from our point of view, it's interesting to compare these kind of hardcore user requirements with what the model can do. As Elizabeth says, we don't claim that the model can do this, but it's interesting to see what might be needed. So these are more kind of operational. So people, they were asked what ice forecasting timescales are most critical to you near ice. And you can see here, they were asked like 0 to 6 hours or down to 1 to 2 months. So most people are saying sort of sub daily. 90% of people want more frequent than 24 or smaller timescales than 24 hours. And 58% of people want more frequent than a daily update. So this is already quite difficult to do for the modeling centers to run the models and to get in new observations. But the sting in the tail really is this one. So they were asked, what's the minimum size of any ice information that you need to know about, whether that be the size of the flow, ridge, lead, etc. And for an optimal solution, half of the people said less than 10 meters. So the sub 300 meters that Elizabeth had on her side is well, slightly optimistic perhaps. So 75% of ships users want information to less than 50 meters. So clearly there's actually quite a role for, oh sorry, I think I've got this. Some requirements will prove very challenging for the sea ice models, but there's maybe a lot of interesting work then to be done communicating that risk. I know that the guys at Environment Canada have done quite a lot of trying to interact with those people. Oh, you don't need that.
Okay, thank you. All right, so I think what that means is that as sea ice modelers, we need to think a little bit more outside the box, or maybe another way of saying it is to think outside the ice. You know, those questions are often focused on the ice, you know, how big of the ice do you, or how small of the ice do you need? But what might actually be useful is understanding where there's not ice or where the ice is weak. And so this is just an example of a product from the US National Ice Center that they base on this ice model. It comes through the Navy. They send their output to the National Ice Center, and then the National Ice Center makes these products. And this is one where they're plotting out the ice strain and the fracturing risk. And so the point here is not to figure out exactly which direction these leads are going or anything. It's just here's the area where the ice is going to be active. You might want to pay attention if you're in that area. Okay. So that's just an example. But these are fairly short-term forecasts. I can't remember what they are. They're like once every, well, they're 7-day forecasts, but they come out more often than that. but these are so short that they do have to assimilate data in here. So they assimilate ice concentration and I think also thickness for these simulations. So now that's the very short term. Now I want to go to the other end, the very long term things, and talk about using these models for planning purposes. And sorry, I just keep doing that. The longer term planning really can only use the larger scale information. And the reason for that is that sea ice is very dependent on the weather, you know, and if you can't forecast the weather out more than a couple weeks, then you're going to have trouble forecasting the details of what the sea ice might be doing. But what saves us in this case is that the large scale changes because of climate change or whatever do produce a signature in the Earth system that we can analyze. And so is Dirk here? I haven't seen Dirk. Oh, bummer. I was really hoping to see him. Okay. Well, I was going to pick on him, so I won't pick on him, but yeah. No, I'm actually one of the 30 authors on this paper, so I'm picking on me. All right. This is a study that Dirk led, analyzing output from the CMIP6 ensemble. And let me know if you don't know what that is. But there's many different models doing climate simulations with a variety of emission scenarios to get an idea of what's going to happen in the future, maybe. And the question that they were asking is, what does CMIP6 say about when the Arctic will become ice-free? Where ice-free has a particular meaning. It's when the amount of ice in the Arctic gets below 1 million square kilometers. We just use that as a, for practical purposes. You have to define it somehow. And so what they found is that, yeah, okay, so by mid-century, the Arctic is probably going to be ice-free for most of these scenarios. There's one that's particularly rosy and unlikely to happen. But otherwise, it seems like the Arctic ice is in trouble in the summer. Okay, so that was the conclusion. I want to dig a little bit deeper into how we got to that conclusion. In this plot, each one of these dots is a model simulation. The colors are the different scenarios. What's being plotted is the year at which that simulation first reached 1 million square kilometers of ice. Okay, so what we see here on the left is basically all the models that were available at the time of the study in CMIP6. And then in this paper, we selected some models that we consider to be plausible, where plausible also has a definition. It means that the model's ensemble spread actually includes the observational record, considering both the trends and the variability. And so you can see that took out some of these simulations, some of the models. But you'll notice that even among the plausible models, several of them thought we should be ice-free by now already. Okay, so but let's see, the numbers up here at the top were the total number of simulations in the bottom row, and then in the top row are the number of simulations that do not simulate sea ice cover less than 1 million square kilometers by 2100. Okay, so you can see, where am I? In the case where all of the simulations are included, there are some that still had ice, a few beyond 2100. In the selected models, there was only one, and that was in one of these particularly rosy scenarios. But the question that I want to ask is, did it matter that we threw out a bunch of the models? What would we have come to different conclusions had we not done that? What was the purpose for doing it? Do we have more confidence in these for some reason? That's the question that I wanted to ask. And I would love for Dirk to be here because he could probably tell me, but I'm not going to go back and reanalyze what we did in this paper, but I was looking at this for a different project where I and some of my colleagues were asked to analyze how sea ice might be changing along potential shipping routes in the Arctic. And this is certainly not the first study like this, not the only one by any means. And so as I was looking at this, I found this paper in Nature Climate Change that analyzed a single model. It has a large ensemble, so there's a lot of simulations there, but it's just a single model. And what they were doing is looking at how access to various towns in the Canadian Arctic might change in these different scenarios. And so I was looking at this going, well, this is CESM. Sorry, Marika. But there are places in many of these models where the navigational routes, you couldn't actually sail a ship through the model because there's land blocking the route, just because the resolution isn't high enough to resolve these little straits. And that's particularly true in the Canadian Arctic. There's land blocking the routes. And so I was like, okay, this paper is saying, well, how are you going to be able to sail to these little towns and things in the Canadian Arctic when you can't actually get the ship through there? Does that matter? You know, that was the question that I asked. And so what we did is we went back to CMIP 6. We used all of the simulations that were available, except for the ones that were not on their native grids, because we were asking a question about the grids. We didn't want to use the ones that have been interpolated to some other grid. But so we used all those models. We chose a few representative paths through the Arctic. There's the Northwest Passage. There's one that you probably can't see very well that goes right down through here, which is the, I'm calling it the North Polar Route. I don't know if it has a real name. And so we looked at we analyzed the access to these with the models that did not have land blocking the routes and compared that to all the models. And it didn't make any difference at all. Statistically, no difference. Just doesn't matter. And so I thought, well, that's a good thing for the Nature Climate Change paper. So I decided to take it a little farther because looking at the literature, there's a number of papers where the authors do select models. They all do them differently. It's different sets of models. And I was wondering, what impact does this actually have? And so these plots over here are comparing, just look at the pink lines for the sake of time. The pink lines are this North Polar Route. So we have a plot that has all of the models that we analyzed. This one over here has 12 models. That's Dirk's selection of models from that paper I just showed you. And then there are a couple of other combinations from this paper where they say, well, these models match the observations pretty well, either for the ice concentration or for the ice volume, or this other combination is where both of those match. And that really reduces your number of models a lot down to 6. Okay, but what I noticed here for this North Polar route is that when you're looking at all the models and for Dirk's combination of models, there's a lot of variability in here, which is not visible in this selection of models. And so that kind of worries me. The plots I'm doing are for the 2050s. We're several decades out in the future. And so this to me means that by throwing out a bunch of models that don't somehow match current day observations, that we're losing information about what might happen in the future. And, you know, and it sort of makes sense because for current day observations, it's always ice covered up there, or at least in the data that they were using. So you don't see that variability. I think the variability is more likely because we're changing from ice concentrations that are essentially 1 for a long time to at some point in the future, there will be no ice in the summer. I'm just talking about summer here. And in between, we don't know what's going to happen. It's not going to be a steady march of the ice edge back toward one side of the basin or toward the middle or whatever. It's going to be over here 1 year and over there another year, and then it'll be over, there's going to be a lot of variability there. And so I think that's what we're picking up in the models here, which we don't see here. And so this is a discussion that I would like to have later, not now, but as part of this workshop, maybe. I do have we'll have a poster out there that shows the rest of this discussion. So any of you who have statistics in your background, which I don't, can help me figure out how to analyze this and present it, I would love to talk to you about it. So I'd just like to leave it at that and say thank you and take questions, and we'll go from there.
Parallel process in case of a Zoom. Thank you much, Elizabeth. Thank you much, Elizabeth. Great overview. So there is actually a scheduled discussion at 4:30 today. Okay, so hopefully you've structured that discussion.
I just set it up.
Right. Okay. If there are any questions, either from the online community or here, please let me know. And I guess my usual point here is like, there are no stupid questions. Okay, so, and there's a lot of assumed knowledge in here, so that's fine.
Bruno,
let me give you the microphone. Bruno, whoa, you need this.
Let's speak.
Given that there's like limited improvement like in computing efficiency and like a numerical like a computing power that we have, can you comment on the effectiveness of increasing resolution versus adding new physics, adding new subgrid scale parameterization? If you had limited resources, where would you put like your in which basket would you put your eggs? And
it depends on what your application is. If you really want to get into detailed processes and that kind of thing, do it, put the parameterizations in, but recognize that those parameterizations might not be run in climate runs because you can't afford them.
Yeah, in climate run, I'm for climate application, what would you say we should do? Applications,
I'm going to get myself in trouble, but I'm going to say that we need to keep the simulations less expensive so that we can do more of them. Because like the last thing that I was showing, you need those big ensembles. I think you need actually multi-model ensembles like the CMIP6 to really capture the uncertainty. Oh, Bruno has another one.
Oh, let me check.
Ian.
Okay, there's nothing on Zoom, so okay, right. Who's next? Yeah, I'm gonna get my steps in today, it turns out. Who am I passing this to? Oh, Ian.
Yeah, thanks. I have a quick question. I figured I would ask while the mic was nearby, but I didn't time it quite right. Really for Ed, I guess. But you showed this thing where you surveyed all these mariners, and they want forecasts with a time scale of like 24 to 48 hours, and they want that data once or twice a day with like a 10-meter footstep. And it just made me wonder, for those uses, is a model-based forecast any better than just knowing what the state is right now, say from a high-resolution satellite image, or maybe using a model for a nowcast? What's the, before we put any modeling effort into answering that, like what's the benefit of having a forecast when you're looking at such short timescales?
You've made this complicated because now Ed needs the microphone. Sorry.
Well, most of the products that they're getting from the ice services anyway are essentially nowcast. They're based on satellite products. They do use some forecast, but yeah, I think that's essentially what the ships are saying, that they want analyses more regularly. But they're still, even for those charting things from the satellites, they're still not going to capture flows of and be able to correctly deliver a forecast on a 10-meter resolution flows. So I think there is an element of they've been asked what would they really like, and they've said it. It's quite ambitious.
That's easy.
Okay. Yeah, that was Sissy.
I just couldn't resist, so that you kept your exercise up today, Danny. But I guess this conversation kind of suggests to me that maybe we should be thinking of models as a tool for downscaling in these kinds of short time scales. And, that's where high resolution could potentially add value if we think that the observational resolution informs that scale. So I'm curious what you think about that.
I don't know how to answer that.
Very good question, I would say.
Yeah,
Possibly higher resolution and possibly higher physics fidelity as well. Yeah, it's an excellent
Yeah.
question.
Ed, I can't hear you. I know the online people can't.
Something about SAR.
I was going to say very high resolution SAR, like the TerraSAR-X satellites or RadarSat constellation, can provide products at 25-meter resolution.
Mhm.
Generally, one has to pre-order those. So a colleague of mine used to work on a ship in Shell, and he paid a member of staff full time to be ordering satellite imagery because they cost about 300 euros per snapshot. But you've got to let them know in advance the area that you need. So yeah, the observations can be useful, but those things
So-
are generally human. They're still developing algorithms to be able to process that data. Mostly it's human analysts. And
So I was wondering if the operational centers like maybe ECMWF actually somehow combine those two. Do you take high resolution observations and combine that somehow with what the model output is? Even like in a weather forecasting sense, where you look at one, you look at the other and say, oh, this is what's going to happen.
I don't want to speak to
Yeah.
but not for CI. It's not at that resolution.
You want on the record? I think we've come to the end of our allocated time, although it's not that crucial. Don't appear to be any questions online. They're not coming through in the chat anyway. So I think that will be plenty of time for
Oh,
discussion
Siobhan had a
later on.
comment.
Oh,
Looks
next
like-
few decades. Oh, here we are. Okay.
Just come past and took photos. There's nobody online with a question. But,
Saiban has made a comment. The next few decades, I agree we need multi-model and large individual model ensembles to understand the levels of year-to-year variability as the ice declines. There you go. She agrees with you.
Vote
Yeah.
in favor. All right.
Yeah, okay.
All right. Well, thank you very much.
Thank you.